Hello everyone, welcome to my YouTube channel EC with Bertha. In today's class, we will see the next portion of the optical fiber communication, that is signal dispersion. As you can see, there are three types of signal dispersion: chromatic, modal, and polarization. Basically, chromatic dispersion is color related. Modal dispersion basically are due to different number of modes, and the polarization due to change in polarization orientation. Let's start with the first, chromatic dispersion, or also called intramodal dispersion. As it is written, it is source-based. It occurs because optical sources emit different band of frequencies and the spectral components travel at different velocity. This causes propagation delay difference between different spectral components. Hence, the first spreading takes place as a result of the fact that group velocity is a function of wavelength. Group velocity is the function of wavelength. Group velocity is the function of wavelength. Intermodal dispersion is combination of material dispersion and waveguide. Intermodal dispersion is a combination of material dispersion and the waveguide. Basically, what is material dispersion? Material dispersion basically arises because of refractive index of the core material as a function of wavelength. Material dispersion arises because of refractive index of the core material as a function of wavelength. This causes a wavelength dependence of the group velocity as a function of lambda wavelength. The value of material dispersion is calculated by this formula, that is delta T material is equal to delta Ts length upon C into Dmat. Dmat basically is the dispersion parameter and its unit is picosecond per kilometer nanometer. We can see material dispersion increased with fiber length. As per this formula, we can say material dispersion increases with fiber length. As I told you, intermodal dispersion is a combination of material dispersion and wavelength dispersion. It can be reduced by using monochromatic source of light. Monochromatic source of light lasers. Chromatic dispersion is fixed for specific wavelength lambda and its unit is picosecond per kilometer into nanometer. This is a point to be noted. That diffraction index, that is denoted by neta, depends upon wavelength, hence it is called chromatic dispersion. We have this beautiful formula. This chromatic dispersion is equal to DC, that is dispersion constant, or coefficient of chromatic dispersion, into DL, that is specific length, whose unit is per kilometer, B, bit rate, unit is picosecond, and then delta L, which is spectral width of light source, and its unit is nanometer. So here's the formula for chromatic dispersion, which is equal to DC, DL, B, and delta L. Basically, waveguide dispersion is due to bending the characteristics of wave, as wave travels faster in cladding than cone, which leads to waveguide dispersion. And we should note that this bit distance product denotes the quality factor of fiber. This bit distance product denotes the quality factor of fiber, and its formula is bit distance product is equal to B, that is bit rate, into L, that is length, which is equal to 1/2 Tc per kilometer. 2 Tc is the bit rate, L is the length of the fiber. So we can write here BL is equal to 1/2C. Okay. Now see the second type of dispersion, that is intermodal dispersion. It is totally fiber based. It is present only in multimode fiber. It occurs due to propagation delay difference between number of modes in multimode fiber. Each mode has to travel different distance with same velocity. Hence, each mode reaches the destination at different time, which leads to broadening of pulses. Basically, maximum delay difference depends on the transmission time of slowest and fastest mode. I said maximum delay difference depends on the transmission time of slowest and fastest mode. Higher the delay difference, higher will be the dispersion. Point to be noted is intermodal dispersion is negligible in single mode fibers. Intermodal dispersion is negligible in single mode fiber, and it can be reduced with the help of graded index fiber for multimode operation. I repeat, it can be reduced with the help of graded index fiber for multimode operation. This intermodal dispersion can be reduced by graded index fiber for multimode operation. And here we have the formula for intermodal dispersion, which is T mode is equal to 440 L upon B mode. And its unit is nanosecond. B mode is the spectral width of source. This B mode is the spectral width of source. L is the length of source. L is the length of source. T mode is the dispersion time for intermodal dispersion. T mode is the dispersion time for intermodal dispersion. T mode is the dispersion time for intermodal dispersion. So we have seen intermodal dispersion. Let's see the third, that is polarization mode dispersion. In single mode fiber only this dispersion occurs. Observed mainly in single mode fiber. The light wave has two orthogonal modes. The light wave has two orthogonal modes, and due to birefringence of material, that is non-uniformity in refractive index. Birefringence of material means non-uniformity in refractive index. There is change in polarization orientation. Of polarized mode. So we can say polarization mode dispersion has a serious effect on the links working above 10 Gbps. It's a point to be noted. It has a serious effect on the links working above 10 Gbps. And the polarization mode dispersion is not a fixed quantity and it varies with wavelength and time. Point to be noted is polarization mode dispersion is not a fixed quantity and it varies with the wavelength and time. We have this important and beautiful formula of polarization mode dispersion, which is equal to dPmd, which is polarization mode dispersion coefficient or constant, into fiber length half or root of fiber length, and its unit is nanosecond. And this dPmd is propagation delay due to polarization mode dispersion. So we can use this formula to solve manual numericals. Let's see this chart, which clearly tells the reason, relation, and the fiber affected as per the different dispersion. Like we can see here, chromatic, that is also called fixed intramodal dispersion. The reason behind this is combination of waveguide and material. Related to color of light, chromatic light source, basically LED, and fiber affected by this is maximum for single mode and the minimum for multi-mode. Second one is intermodal dispersion. Intermodal dispersion, the reason behind this is propagation delay difference between modes. Propagation delay difference between modes is a relation, and the fiber affected is multimode fiber. Third is polarization model or not fixed, it's basically random. The reason behind this is the presence of orthogonal modes and bi-direct fringes. Changing polarization due to bi-direct fringes of material is the relation given by polarization mode dispersion, and the fiber affected is single mode fiber. Let's see the rise time. Rise time is used to find dispersion limitation and response of optical system. We have this important formula, that is T system, which is system speed. This T system is system speed is equal to under root of transmission time square plus model dispersion rise time square plus chromatic dispersion rise time square plus polarization mode dispersion square plus receiving time square, which is equal to delta T total, that is total dispersion, and its unit is nanosecond. These are the elements basically that limits the speed. We should be noted that T receiving is equal to 350 upon BRX. Here TRX is the rise in nanosecond and BRX is the bandwidth in megahertz. This BRX is bandwidth in megahertz. First, cloning in a fiber is sum of all effects occurring inside the fiber. Hence, delta T also is equal to under root of T mod dispersion square plus T Morse square plus T chromatic square. Maximum bit transmission rate for no overlapping is given by this. B is less than 1 upon 2 TR, where TR is equal to under root of TT square, that is transmitted pulse per square, plus delta T total square. And also, we should note that data rate is indirectly proportional to distance, which is in kilometer. And the point to be noted is in single mode fiber, T mode, that is modal dispersion, is equal to 0. And the second one, as the data rate goes up, the distance goes down. As the data rate goes up, the distance goes down. Let's see another concept, as we have covered all the three signal dispersion very well. Now see the link design concept. Basically, link design. Let's take our transmitter, which have the power PS, source power. This is the low set connector, which goes to media or channel, that is optical fiber, and then to the receiver, which have the connected receiver as well. So by this arrangement, we can calculate different things like splice loss.